This lecture will focus on the problem of preventing overfitting when training classifiers. So we're going to take a look first at how we can score the performance of binary classifiers, and then we're going to go a bit beyond that train validation test scheme that we saw previously and look at cross-validation as a better way of selecting models and selecting hyperparameters such as regularization, weights, and so forth. And we're going to focus on logistic regression. This is the classifier that we covered last week. And we're going to look at model selection and regularization with logistic regression. So let's start with this problem of how to score the performance of a classifier. We saw that for regression, we were minimizing the sum of the quadratic errors, and we could use the same sum of quadratic errors as a measure of the performance of the hypothesis that we obtain. So we can use the predictions for a set of examples, for example in the test set, and compute the difference between those predicted values by our hypothesis and the target value, compute the square and add everything up, or we can take the mean of the quadratic error if we divide this by the number of points in the test. With logistic regression, we saw that, again, going by maximum likelihood, we try to maximize the probability of the data, assuming that our hypothesis is correct. And this, because with logistic regression, we're trying to predict the probability of belonging to a class, led us to a different cost function. So this is this logistic loss that we were computing, where all these Gn are the predictions of the probability of belonging to class 1 by the model that we're trying to fit. So for each particular hypothesis, we set a set of parameters here on the W's, and then we can compute the predicted probability using that logistic function, and doing this for the whole set will give us the logistic loss for the set of data that we use. During training, we are using the training set in order to select the best hypothesis by fine-tuning these parameters. After training, we have one hypothesis, and we can, for example, apply this to the test set and have a measure of the logistic loss for the test set. However, this may be not very useful because intuitively it's not a measure that is very easy to understand. So generally for classifiers, we can use different scores for evaluating. So we use this logistic loss or cross entropy to optimize the parameters and find the best hypothesis. But then we can look, for example, at the error between the predicted probability and the actual class. So if we have a point of class 1, we would like the predicted probability of belonging to class 1 to be as close to 1 as possible. If the point belongs to class 0, we would like the predicted probability of belonging to class 1 to be as close to 0 as possible, because the point does not belong to class 1. So we could use the Breyer score, which is the same idea as the quadratic error that we used for linear regression, for example, but now not applied to the actual distance between the discriminant and the point, because we saw this does not make much sense, but applied to the difference between the predicted probability, which is what we are getting from our hypothesis in logistic regression, and the actual class label, which can be 0 or 1 for each example. So basically, we can compute a mean quadratic error between the predicted probabilities and the class labels. This is called the Breyer score, and gives us a more intuitive notion of how off our hypothesis is relative to these points that we are evaluating. But we can imagine this. So let's look at this probability for a given hypothesis in logistic regression. We can represent it like this. Suppose that we have x vectors of 2 coordinates. These are the features. For each of these points, we predict one value for the probability of belonging to class 1. For example, in this region here, the probability is very close to 0. Then it starts increasing with that S-shaped curve of the logistic function. And for this region here, the predicted probability is close to 1. And now we can also plot our data where we represent the points of class 0 here at this plane, at the 0 level, and the points of class 1 at this plane here. So the difference between this surface and the points would be the Breyer score. We get the mean of the quadratic difference between those two, and this gives us the Breyer score. But then there are other things that we can use for classifiers in general, even if we do not have this prediction of the probabilities of belonging to a class. And this may be more useful because then we can use the same measures, the same performance measures for all classifiers, regardless of the algorithm that we're using to obtain the hypothesis or what the model is and so on. So one way of representing the performance of the classifier is using a confusion matrix. We can consider that the different rows represent the different predictions. For example, in this first row, we are predicting the points belong to class 1. In this row, we predict the points belong to class 0. And in these two columns, we have the actual class of the points. So if the point belongs to class 1, and our hypothesis is predicting that the point belongs to class 1, this is a true positive, which means that it is predicted as a positive, and it's also really the positive example, class 1. If the point belongs to class 0 and our hypothesis predicts it belongs to class 0, this is the true negative. The point is negative, but and we are also predicting it to be a negative, so it's a true negative. As you can see, the diagonal here, if we count the number of true positives and the number of true negatives, the sum of this diagonal will tell us how many examples are being correctly classified by our hypothesis. Off the diagonal, we have the mistakes. So in this case, our point belongs to class 1, but our prediction is that it belongs to class 0. So we are predicting a negative, but it's not negative. So this is what we call a false negative. And in this case, it's a false positive because the point is not positive. It belongs to class 0, but we are saying, our hypothesis is saying it's positive. So our hypothesis is giving us a false positive. So this is one way that we can look at the performance of the classifier without having to worry about what exactly the classifier is doing. So we can apply this to any binary classifier and build this confusion matrix for the classifier. However, one disadvantage of this is that it does not give us one measure of performance. It gives us the counts of all the mistakes and all the correctly classified examples for the 4 different combinations here. So we can look at these values and extract some measures that gives us an indication of how well the classifier is performing. For example, the accuracy is a very intuitive measure, which consists simply of adding the diagonal, which are the cases where our classifier is giving the right answer, and dividing by the total number of points. So basically, the true positives plus the true negatives divided by the size of the data set that we're using. This gives us the fraction of correctly classified examples. So if we have an accuracy of 90%, it means that 90% of the answers our hypothesis is giving us are correct. However, this does not give us any information about where the mistakes are. So those 10% could be either in false positives or in false negatives or any mixture of the two. So we can use these different measures to focus on these different aspects. Precision gives us a measure of how trustworthy are the predictions of our hypothesis when the hypothesis tells us it found a positive example. So this is a true positive, the number of true positives divided by the number of examples our hypothesis is telling us are positive. So if, for example, we have a precision of 90%, it means that if our hypothesis is telling us this example is positive, then there is a 90% chance it's telling us the truth, because there are only 10% false positives. However, it does not tell us how good our hypothesis is at finding the positive examples, because it may happen that our hypothesis almost never tells us an example is positive. So that's why it makes little mistakes, because it's very conservative. We have the reverse of this, which would be the recall. The recall is the number of positive examples our hypothesis is stating are positive, divided by all the examples that should be positive. That is, those our hypothesis is getting right, saying they are positive, and those that our hypothesis is falsely saying are negatives, because they are in truth positives, and our hypothesis should be labeling them as positive. So this is the recall. It's the ability of capturing, of finding the positive examples in our data set. So you can see precision and recall are measuring two different things. Precision is how true our hypothesis is, or how often it gets the prediction right when it tells us some example is positive. And recall how often our hypothesis gets it right for all the examples that should be positive. So if you have a high precision, you can have confidence when the hypothesis tells you the example is positive. If you have a high recall, you can have confidence that the hypothesis is capturing all or nearly all the positive examples. So we can compute a harmonic mean of these two scores. For example, the F1 score is the precision multiplied by the recall divided by the sum of the two, or we can decompose it like this. So basically, this looks at a balance between precision and recall, because often the case, more precision can be gained at the cost of lower recall and vice versa. And we can see that if we consider changing the threshold of our classifier. So remember that with the logistic regression, we decided to split the categories in our prediction at the 0.5 probability level. That is, if the probability of a point belonging to class 1 is above 0.5, we label it as class 1. If it's below 0.5, we label it at class 0. But we could, more generally, use any threshold value between 0 and 1. For example, if we lower the threshold from 0.5 to 0.1, then all of this part here will be considered class 1. Everything above probability 0.1 would be considered class 1, and below class 0. If we increase the threshold, then we start becoming more demanding for classifying something class 1, then everything up to probability 0.9 would be classified as class 0, and only above probability 0.9 would be classified as class 1. So it's intuitively obvious here that if we lower the threshold, we start getting more positive predictions. So this means we'll also get more false positives, but we will not lose some true positives there. For example, these red dots here, if they would be positive examples, if we lower the threshold, we do not lose them. However, we start getting these as false positives. If we go the other way, if we increase the threshold, then we no longer have these points as false positives, because now we will label them as class 0, but we will lose these as true positives. So basically, if we increase the threshold, we decrease our ability to recall points, though we increase precision because we have fewer false positives contaminating our predictions. But if we lower the threshold, we increase recall because we don't lose the true positives, but we decrease precision because in our predictions we are getting false positives more often. So we can look at it like this as we vary the threshold. So let's say we take a threshold at 0. This would be one extreme. This means that everything is classified as positive because all the points have a probability 0 or more of belonging to class 1. So we have we get right all the positives. We have all the true positives there, but we also have all the negatives as false positives, because we are saying that everything is positive. So this is not a very good threshold for classifying. As we start increasing the threshold, we start eliminating false positives, because we start drawing lines here that start discarding these negative examples, and we no longer consider them falsely to be positive. However, at some point we start losing true positives. So we start losing these red points here as we increase the threshold. And eventually, if we place the threshold at 1, we have 0 false positives. We make no mistakes on this case because we are considering everything to be class 0, but we also have 0 true positives because we are being so demanding that we don't classify anything as class 1. So you can see intuitively that when we look at this progression here, the greater the distance between these two lines, the better our classifier is, because the more true positives we can get after reducing the amount of false positives. So this is the idea of the receiver operating characteristic. This curve, receiver operating characteristic curve, has a strange name because this was initially used during World War II to assess the performance of radar operators in distinguishing between enemy airplanes and interference like clouds or flocks of birds and things like that that could also be spotted on the radar. So we had this problem of false positives and false negatives that were needed to balance, and the receiver operator was the person that was operating the radar machine, and each curve here would be characteristic to each person because of the way they would balance false positives and false negatives. So the name stuck, and now we use these ROC curves for general classifiers, even though the name no longer has anything to do with the kind of classification problems we are solving. But the idea is that by changing this threshold, we can see for each case what is the number of true positives and the number of false positives. For example, for a threshold of 0.2, we have these false positives and these true positives. So we can now plot one against the other. Here in the x-axis, we have the false positive rate, and in the y-axis, we have the true positive rate. So this tells us how many true positives we can have, or what fraction of true positives we can have if we still have 0 false positives. If we allow a few more false positives, then we have more true positives here. And at some point, we reach the maximum of true positives, and then we can keep increasing the false positive rate, but no longer is useful that. So basically, this diagonal here would be a completely random classifier that would give us 50-50 chance of getting right, which means that as we increase the false positive rate, we would also be increasing the true positive rate, and we simply had a diagonal like this. So this would be the baseline of just flipping a coin to decide on which point what to do. The greater the area under this curve above this diagonal line, or we can measure the whole area under the curve, the better our classifier performs, because it means that even if at the cost of few false positives, we can have a large increase in the true positive rate. So the area under the ROC curve is also a measure that is often used to assess the performance of classifiers. So basically, for logistic regression, we can use either the loss function or the Brier score. The Brier score can be used whenever you have a classifier that gives you a probability prediction, which you can compare with the actual class labels. The logistic loss function, of course, we can use because we are using that for training. We can also use that for assessment. The drawback is that this is not a very intuitive function to understand, for us to get a feeling of how well the classifier is performing, and this only applies to logistic regression. So if you have to compare different classifiers, you would have different loss functions, and that would not make it easy to compare. These kinds of things, precision, recall, accuracy, the confusion matrix, the ROC curve, and so on, these you can apply to any classifier in general. So these are good measures for assessing your classifiers because they can allow you to compare with other classifiers. In scikit-learn, there is a standard interface for the classifiers, so all classifiers contain a score method. The score returns the accuracy, that is the fraction of correctly classified examples. So if you want to do a logistic regression, you just import the logistic regression from the linear model module. You create an object for the logistic regression. If you want to insert other arguments there, you can, to change for example, the regularization parameter and so on, but you can just use the defaults. You call the fit method to compute the parameters, to train the model and get the best hypothesis. And for this, you need to provide the features, the X matrix, where each row is an example and each column is a different feature, and the labels, the vector with the labels that you want. So the zeros and ones for the class labels. And then if you want, you can apply after you call fit, this object is now trained, this model is trained, you have the best hypothesis there from the training set, and you can apply this to another set, for example, the test set, just to score, and this would give you the accuracy. So this is the fraction of correctly classified examples. If you want to measure the error, that is the fraction of incorrectly classified examples, you can do just 1 minus score, and this will give you the fraction that were not correctly classified. So this would be the general scheme for using these classifiers in scikit-learn, and we will be doing this a lot as we see different classifiers in the future. So you can do this approach in general for classifiers in scikit-learn. And now let's see how we can go a bit beyond the simple train, validation, test scheme that we saw last week in order to deal with overfitting, either by selecting the best model or by adjusting the weight we give to regularization factors. So previously we split our data into 3 sets. We used the training set to find the best hypothesis by minimizing the training error. Since the training error is now very biased because of our choice of our hypothesis, by minimizing the training error, we measure outside the training set with a validation set. We measure the validation error in order to compare different models or to compare, for example, the result of using different regularization weights. And then after using the validation error to select the best model, or the best hypothesis in this case, because we are always validating the error on each particular hypothesis, we can use the test set to estimate the true error, because in this case the test set, since we are not using it for any decision, gives us an unbiased estimate of the true error. Now, one problem here is that we are selecting the model based on just one estimate for one hypothesis, and using only one sample, the validation set. So as you recall, this has some noise, some randomness associated with it. So depending on using different points for training and validation, we can get slightly different hypotheses because we are using different sets of points for training, and we also get different measures of error because we are also using different points for validation. So if we do this once, if we split training and validation once, we are only looking at those particular hypotheses that were created using that training set and measuring the error only on those samples on that sample that we chose for the validation set. So this is a bit noisy and it's not as reliable as it would be if we could just average over different sets. So this is the idea here of cross-validation. We are going to select different hypotheses from the same hypothesis class, that is using the same model, using slightly different training sets. And then we're going to measure the error outside the training set for each of these hypotheses and average that validation error outside the training set. And we're going to do this by splitting the training set into a number of folds, a number of partitions, and then we're going to average the validations. If we split it into K folds, we have K validations. In each case, using one fold outside for the validation and the remaining folds, the remaining K minus 1 folds for training. So instead of doing a first split into training, validation, and test, we split out the test set because we're going to leave that one to the end without using it for anything. And we do this cross-validation on the training set. So I'm going to show it schematically to make it easy to understand. Suppose that we took from our data set, we left out a set of points for testing, and this is our training set. So the points that I show here are our training set. We are now going to split them, our training set into 5 folds, and we're going to use this first fold here, the ones that are larger, for validation, and the rest for training. So the small points here are used for training. We are training this classifier here, and now we're going to compute the validation error on the large points. In this case, there are no errors on the large points, so we have a validation error of 0 here. And now we move on to the second fold. So now this group here is going to be left out for validation, the large ones again, and all the others, the small ones, are going to be used for training. So you can see that the hypothesis is now slightly different. The curve is not exactly the same, and now we also get a validation error there, and now we keep doing this. So at each point that we do this, we get a slightly different curve. At each point, we are using different data points for validation here outside. So we get different values for the validation error. And this is the result of this 5-fold cross-validation. We trained our model 5 times using 5 slightly different training sets. So we get 5 different hypotheses. For each of these hypotheses, we used a set of points outside the training set for that hypothesis to measure the validation error of that hypothesis. So this gives us a set of different validation errors for different hypotheses using different points. And we can now average this, and computing the average using cross-validation, we are averaging these validation errors of several hypotheses. So we are reducing the effect of that randomness for getting each sample. We are not getting, when we compute this average, we do not get an estimate of the true error of any specific hypothesis because we are averaging over different hypotheses, but we get an estimate of the true error for the model when it is trained on this kind of data. So if we average these values here, which are the validation errors of the different hypotheses, we get an estimate of what, on average, is the error that our model will give us in the hypothesis we obtain when we train it on this kind of data. So this would be, in a sense, an estimate of how this model will perform on this kind of data when we train it and obtain the best hypothesis. And this is a better estimate than using training and validation because if we first train with just one set, for example, here, if we just train with this set of points and then validate with this set of points, we only get one estimate of the true error for one particular hypothesis and not a good estimate of what, on average, the model performs here. So this cross-validation is generally better because it gives us a better idea of how to evaluate the performance of our model on average on this kind of data, on the kind of data that we're using. So what we're doing here in cross-validation is splitting the data into K-folds. This is K-fold cross-validation. We train our model with all folds but one, leaving one out for validation, and then we repeat that K times and average the validation error. So if we use as many folds as we have data points, this you can do if you have very few data points. This is called leave one out cross-validation. For example, if you only have 20 data points, you can split into 20 folds. This means that you train with 19 points and leave the first one out. Then you train with other 19 points, leaving the second one out, and so on and so on. And so just leave 1 point out at each iteration. Now, one problem here that sometimes we have is class imbalance. Unless you have a very large data set, it may happen that when you do something like this, you could end up having, for example, only red points in one of these sets, or a much larger or a large imbalance in many of the sets, and so on. So this is not very good. If, for example, you are trying to compute the validation error and you only have points belonging to one class, or if you're trying to train and most of the points just belong to one class. So one thing that we can do is to use stratified sampling. In stratified sampling, you sample at random, but still preserve the proportions so that each of the folds will keep the same proportion of the both classes that you have, in order to avoid this in different folds getting very different proportions of classes. If you have a very large data set, simply selecting by random will be enough, because it will be very unlikely that you'll have an imbalance in different folds if there are many points. But if you have a relatively small data set, then you can use stratified sampling to help with this problem. Okay, so let's see an example of model selection for classifying with logistic regression. So we want to find the best model for classifying these data points here, and we're going to start by loading the data, shuffling, and standardizing the features. Now, shuffling is important here when you are splitting the data into subsets, because you never know how the data is sorted in the file. For example, if you have all the red points first and all the blue points last, if you don't shuffle it and you just split the data into folds, for example, then you will get folds with only red points and then folds with only blue points, and things will not work well using that. So we're going to import shuffle from scikit-learn utils. This one works a bit differently from the NumPy shuffle. So instead of doing shuffle in place, it returns a copy of the matrix that we provide, but shuffled along the rows. But you can use it like this. So basically, we load the data from this file. It just has the X and Y coordinates on the first two columns, and then a 0, 1 label on the last column indicating the class of the points. And now we're going to separate this. We're going to, the first column has the 0, 1 label, and the last two columns have the coordinates. So we have that here. The first column is the labels. This is the Y's vector with the 0, 1 labels. And this is the X matrix with the coordinates, which are the features we're going to input into our model. Now we're going to standardize, so this means computing the mean and standard deviation, and then subtracting the mean and dividing by the standard deviation, so that each feature, each column of our data has a mean of 0 and a standard deviation of 1. So everything is there centered around 0. And now we're going to want to try different models for logistic regression. Now remember that logistic regression is a linear classifier. So we cannot really do different models if we just put in x1 and x2, the two features that we have, because it will always do a linear classification. But we can consider different models by expanding the data into higher dimensions. And so we are training a linear classifier in 2 dimensions, or a linear classifier in 3 dimensions, 4 dimensions, and so on. And these are different models because they are representing different hypothesis classes. In 2 dimensions, they are representing lines. In 3 dimensions, they are representing planes. In 4 dimensions, hyperplanes, and so on. So we can do this expanding the data polynomial to a number of features, where we start with, we're going to increase by 14 features our initial data. So we create a matrix of zeros that has many rows as the data that we have, and as many columns as the data that we have originally, plus 14. So these will be the expansions we will add. And we will just copy the original data into the first two columns, but then we're going to add a third column with the product of the two features, then a fourth column with the square of the first, another with the square of the second, then the cube of the first, then the square multiplied by one of them, and so on. So note that all of these transformations are nonlinear transformations. We are doing products or exponentials and such, not just linear combinations, because that would not be useful. So we are creating additional features that when we transform our data into that higher dimension, our data points will be spread out into curved surfaces. So when we use the linear classifier, the intersection between the linear discriminant and those curved surfaces will end out being a curved line in the original space. So this is what we saw last week. It's the same approach. And now we can start with our original data and just expand it into all of these features. To separate between train and test, we don't need to do this ourselves by hand. We can use the train test split from the model selection module in scikit-learn. So using this, you give the matrix of features, the vector of the target values, the labels. You say what is the size of the test set. In this case, we're going to reserve 1/3 for testing, and you can also stratify. So you're going to do stratified sampling on the class labels to ensure that the proportion of zeros and ones in the class labels on our test set is the same as on the training set, or as close as possible to that. And now we're also going to generate the folds using K-Fold. You can use K-Fold like this. So suppose that you have some data set here. You can create an object of the K-Fold class by specifying how many folds you want to create. And now you use this object, the split method of this object, to iterate through training and validation sets. So this illustrates how this works. We just say that we want K-folds with 4 folds, with splitting into 4. And now when we give this vector here for splitting, we get the indexes for which elements we put on the training set and which on the validation set. So this tells us first to use the first 3 elements for the training set, for the validation set, sorry, and the remainder for the training set. But then it exchanges, uses the 3, 4, 5 on the validation set and the others on the training set, and so forth. So it gives us, it iterates through 4 iterations, and at each iteration it tells us the indexes to use for training and validation. Adding this array here is just to tell split how many data points we have. So what we get here are always the indexes, and we can use those for the matrices and so forth. You can also use stratified K-fold. In this case, you need to give 2 arrays, one for the split to know how many elements you have, and the other with the labels for stratification. So for example, suppose that the labels look like this. And so here we have the first 3 elements are in the validation set, then the next 3, 4, 5 there. But then here you have some change, because we have this in the first fold, this in the second fold, and then this will only have 1 of label 1, and this last will not have anything of label 0. So in order to avoid this, the stratified K-fold is exchanging the element of index 9 with the element of index 8 in these folds. So if you want to prevent these kinds of messy results where you have a large class imbalance in different folds, you can use the stratified K-folds and add as the second argument the class labels, so that the split is done in a way that tries to, as well as possible, keep a balance between the different classes in all the folds. Okay, so let's use this for our example, for our logistic regression. We are going to create an auxiliary function here just to compute the errors, the training and validation errors for each fold. So we receive a matrix with all the features. We receive the number of features, the matrix with all the features in our expansion, the labels for the class, and the indexes of the points to use in training and validation. This is the regularization parameter. We're going to use a very large one, which translates to nearly no regularization. I'm going to explain this a bit more in the following slides, but we can just ignore this one for now. So we're going to create a logistic regression object, and we're going to fit it by using as the training set the rows with the indexes corresponding to the training set for this particular fold. So if we are doing cross-validation, we will have vectors like this to specify the indexes for training at each iteration of the cross-validation. And we're going to use the first columns indicating by this number of features argument. So if you are using 6 features, we're going to use the first 6 columns in this model. And this would be for the features, and this would be for the target labels. So the target labels are the Y vector, and we're going to use the same points for the target labels as we are using for the features. This is important because if we don't use the same points, everything will be incorrect. Now we can compute the Breyer score for this. If you want, you can just use score from the linear regression method, and it gives you the accuracy, but we can also do the Breyer score easily because for this particular model, for the logistic regression, we have this predict probability method that gives us the probability of belonging to class 0 and of belonging to class 1. So basically what we want is the probability of belonging to class 1, which is the second column in this matrix here, for all the points. We can compute this for all the points in our data. And now we can just compute the square of the error between each predicted probability and the class label for each point. So the training error using the Breyer score will be the mean of these squares for the training points. So the values corresponding to the indexes of the training set, and the validation error will be the mean for the validation points. So this way we can quickly compute the Breyer score for the training set and for the validation set for each iteration on the cross-validation. Okay, so now we're going to do 10-fold cross-validation. We create a stratified K-fold object here for 10 folds. And now we are going to iterate through different number of features. We're going to start with 2 and go all the way to the end. And for each number of features, so for each model we are trying, we're going to try one in 2 dimensions, then in 3, 4, 5, and so forth. We're going to start with the training and validation error of 0 and keep adding the training error and validation error for the 10 folds that we're doing here. So we're going to take the class labels, the vector of class labels, to stratify on the class labels. This will make it so that the different folds have approximately the same proportion of 0 and 1 examples. We're going to call the calcfold function there to compute the training and validation error we obtain using this number of features and this particular fold, so these indexes for training and these for validation. We're going to keep adding these errors for all the folds. So at the end, when we compute for the 10 folds, we have the sum of the training error and the validation error over all the 10 folds. So now we can just print out for this number of features, we have this average training error in cross-validation and this average validation error in the cross-validation over those 10 folds. So these are some examples. If we use two features, here are 10 lines corresponding to the 10 folds, the training error and validation error. So you see training and validation error are very similar. The different classifiers we get are also very similar to one another, and we miss out quite a few points because we're trying to use a straight line. This is a linear classifier in 2 dimensions to separate these points which cannot be separated with a straight line. If we do an expansion for 3 features, for example, now we added the product of the 2 features, we are doing this in 3 dimensions, and then 4, 5, and so on, and we start getting a larger curvature, more curvature on this discriminant, because remember, in this case with 9 features, we are applying a linear classifier in a 9-dimensional space after doing this nonlinear transformation with our data. So our data now is all bent and twisted in 9 dimensions, and when we project back again the classification into 2 dimensions, we have these curves. We can also see that we have a more diversity, a greater variation in these curves as we go into higher dimensions. We note that the training error now is low because we can easily train our model to classify the training set without errors. The curves are, the lines are flexible enough for that, but we have a validation error here. So when we generalize outside the training set, we start having some errors. So, and if we increase too much the features, we start having a larger validation error. So we can look at it in this way. We can plot the training error and the validation error for the different number of features that we are using in the expansion, and we can note that when we do the cross-validation, so remember that this is an average over 10 validations, this is an average also over 10 folds for training, so this would be the cross-validation error in red, and we see that our best model seems to be the one with 9 features. That is, using 9 features on this kind of data, on average, gives us a lower validation error than for all the other options. So this would be a way of selecting the best model. And if we do that, now we train on the whole training set. So this is an important detail for cross-validation, is that whereas in trained validation set, we always train on the training set and not on the validation set, with cross-validation, we are actually reusing the training set for training and validation in different combinations. So once we get the best model here, this error is actually the average of 10 different hypotheses trained with 10 different subsets of data from the training set. But now we take the whole training set and retrain the model with the whole training set. So we are using the 9 features and the complete training set to train the model, and we can now estimate the error outside the training set, so the true error, using the test set. The test set is that set of points that we split out at the beginning and did not use for anything. So remember that after cross-validation, you have to train your model with the complete set, because what you got during cross-validation was just different hypotheses obtained training with different training sets. So if you want a final hypothesis for your classifier, you need to train the model with a complete training set. So this is basically what we do. We're going to start with any preprocessing we need. Typically, you're going to shuffle the data because you never know how the data was sorted and what kinds of correlations there can be in your data set. You can often normalize or standardize. This is also a good idea to avoid dealing with very large numbers and to help us have some intuitive notion of errors like the quadratic error, things like that, when you're doing regressions. Remember that in classification, you do not normalize or standardize the class labels. That would not make sense. But in regression, it's useful to do that for the target values that you're predicting to avoid problems of having very different scales. We're going to reserve a test set. If you want to have an unbiased estimate of the true error, you need to reserve a set of points that are not going to be used for any decision, just to have that unbiased estimate of the true error. And we're going to do cross-validation by partitioning the training set into n folds, and then doing for each of these folds, leaving out one fold and training with the rest. We're going to measure the validation error, and we're going to average over all the n folds. This can be done to select the best model, for example, and if you suspect that you can have imbalances because you don't have many data points, you can use stratified sampling in both cases here. After we do cross-validation and select the best model, now we need to obtain the final hypothesis. And so to obtain the final hypothesis, we're going to train the best model we selected here with the whole training set. And this gives us the final hypothesis, our classifier, which we can now use on the test set to get an estimate of the true error. Note that cross-validation error would be unbiased if we just measured it. So if we look at this, each of these points is an unbiased estimate of the true error, which means that they can be above or below, with equal probability, above or below the true error. But the problem is that when we look at all of these and pick out the smallest one, this procedure of taking several points that are affected by randomness and picking the smallest one makes the whole thing biased, because odds are that we have picked one that fell below the true error. So that's why we need the test error at the end. Even though each individual estimate of cross-validation error is unbiased, the final result of choosing the best one becomes biased because we are using it to select the best model. And so we need this test set that we never use to make any decision to give us the unbiased estimate of the true error. Okay, so let's see another possibility for handling the overfitting problem. Instead of choosing different models, we can adjust the way the model is trained in order to discourage it from overfitting the data. So we can use, in logistic regression, we can use the L2 norm regularization like we did with linear regression, which means that we're going to add to the loss function a term that is some constant multiplied by the sum of the squares of the parameters, those W's that we're using. Actually, in scikit-learn, we have this C parameter that we saw for regularization that corresponds to 1 over lambda, or lambda is 1 over C. So if we have a very large C, we have a very small regularization, a very small weight given to this term. If we have a smaller C, we have a very large weight for the regularization. The reason for this, for using this 1 over C here, it will become clearer when we look at support vector machines, and it's a way of standardizing these kind of parameters in the scikit-learn interface. But just remember for now that lambda here, the weight given to regularization, is 1 over C. So large C means small regularization, small c is large regularization. Now, with ridge regression, which was regularization used in linear regression with a quadratic error, this was intuitive because if we keep the parameters for our regression, our linear regression, small, we have everything, even the curves that we obtain if we do those expansions, or if you imagine the hyperplane in higher dimension, will be much stiffer because we are trying to keep everything with a small value here. For logistic regression, this seems strange because we have this logistic function here. We are trying to keep the parameters that we are using on this function small, and it's not as obvious at the beginning why this should work as regularization. So let's look at the effect of trying to keep these parameters here small. If you remember, we are trying to find this discriminant, this linear discriminant here, that is determined by the plane that is the inner product of all these parameters, including that W0. I'm just putting everything here to simplify, where the inner product is 0. So when we change the parameters here, just the magnitude of the parameters, this would not make a difference on the discriminant. It just would change the size of the vector here. So we could increase the vector or decrease the vector, and the discriminant would be the same. So if we look only at the discriminant, it's not clear what we can gain by trying to shrink the size of these parameters. In other words, to shrink the size of this vector, because it would give us exactly the same discriminant. But this becomes clearer when we look at the logistic function itself. So that function that is giving us the probability of belonging to class 1. If we have a very large values for the parameters here, so imagine this is only one W and only one X, so we are looking only at one dimension. If we have a very large value here, then as X goes from this value close to 0, below 0, and this one above 0, but in a very narrow interval, this term will quickly change, and we go from close to 0 to close to 1 in an abrupt step. So if W is very large, the logistic function can be very steep. If we lower the values of W, so if W becomes smaller, then the slope here becomes smaller, because now we need to change X by a larger factor in order to go from 0 to close to 1 on the logistic function. So the idea here is that if we decrease the size of this vector, even though the discriminant could be on the same position, it could give us the same discriminant, we are decreasing the slope of the logistic function, so making it span a larger interval going from 0 to 1. So let's see this graphically. Suppose that we have this data set here, where we have points with class 0 here in blue. We have also this point here in blue, and then we have these points in class 1. Now, this is probably an outlier, and it's intuitively overfitting to try to put the frontier over here, because it's quite possible that we will have a mixture of red and blue points over here. So we should not trust this point so much as to put the frontier there. So this could be overfitting, and this can happen if we don't use regularization, because the logistic function can be very steep, and we can go all the way here with a value close to 0, and then quickly jump to 1, and then go on this side with a value close to 1. If we add regularization, then we need to go smoothly from 0 to 1 over a broader range. So this line would be 10%, 25%, 50%, and so on. So as you can see, we are increasing here slowly. We reach the midpoint here, and then we keep increasing slowly until we get close to 1. And if we do this, it no longer pays to put the 50% line on this position, because that will give a lot of error on this side, since we are slowly increasing the value to approximate 1. So this will move the discriminant, which is this midline here, inside this region where there are fewer points, so that the error on this side and the error on this side gets reduced. So this way, if we decrease the size of the magnitude of those parameters, we can force the logistic function to have a smaller slope, and so push the discriminant away from outliers like this, in order to try to optimize the error to where the majority of the points are. So we can try this by picking a model that is clearly overfitting. Note that there is no use in using regularization if your model is underfitting, because if the model itself is not capable of adjusting to the data, then adding an additional term to try to make it stiffer will not help. You cannot improve the model that way. But if the model is adjusting too much to the data, for example, the 15 features model here that has a large cross-validation error and adjusts too much to each training set, we can try to use that model and experiment with different regularization factors. So this is the logarithm of base 10 of C, so 10 raised to -5, -4, 1, 1, and so forth. And we compute the training error, and the validation error using cross-validation. So remember that each point on this line is the average between the 10 different folds that we are using to experiment with different values of regularization. And we can see that things go down, the cross-validation error goes down here, and then it starts increasing a bit again. So we can, as we have a very high C, so this would be very strong regularization. It clearly overdoes it, and we get our model in underfitting because we are putting too much regularization and it cannot accompany well the data. Then as we decrease regularization a bit by increasing the value of C, we start reducing the training error, but at some point the cross-validation error also starts increasing a bit. So if we take too much regularization, we start having too much flexibility. So now we can experiment with 15 features, but using a C of 10 raised to the 5, so 100,000 in the C. This gives us 1 over 100,000 for the weight of the regularization term, so this lambda here. So this would be a small addition of regularization, but it's enough to make the line a bit more stiff and give us a better performance. So in this case, it even happens to have a 0 test error. We not only could manage to classify correctly all the training set, but even when we now experiment on the test set, which we never used during this process, we have the final hypothesis from the training set, and it also gives us 0. So this would be, it actually gave us the best result of the two. Okay, so just one quick note on this data expansion. So this thing that we are doing here to compute, to have these different models in different dimensions, we are doing this by hand to help you understand not only this principle of expanding data with nonlinear transformations, because it's a basic principle that is important in machine learning, but also because we are just looking at these linear models, logistic regression, and so if you want to try different models here, we need to expand the data into higher dimensions and use the linear models in higher dimensions. But I wanted to point out that this is really not something that you'll do in practice, because if you need to do this kind of expansion into a higher dimensional space or nonlinear transformations of the data in order to enable a classification, then what you're going to do is either use something like support vector machines, which can do this implicitly, or neural networks that can do this in different layers and so on. So we're going to see these classifiers later. I just wanted you to know that we are doing this expansion manually now because we are focusing on the ideas, on the principles, and this can help you understand these principles. In practice, if you want to do a nonlinear classification, you're generally not going to do this by hand on your features. You just use another classifier that does this more efficiently, and you don't have to bother doing this yourself. Okay, so to sum up for this lecture, we saw different ways of scoring, evaluating classifiers. So general ways like precision, recall, accuracy, the ROC curve, and so on, that you can apply to all classifiers, or some more specific ways. For example, for logistic regression, you can compute the Breyer score because it gives you explicitly a predicted probability, or you can use even the logistic loss for the logistic regression. However, generally those more abstract ways of evaluating models that you can use in different models tend to be best because they are more intuitive and because you can use them to compare different kinds of models. Then we saw cross-validation. This is a very important idea. You use the training set to do both training and validation. So basically, you start by splitting it into that number of folds. You leave one fold out for validation and train with the rest, and repeat this for all the different folds. And when you average the results, you get an estimate of the true error that, on average, this model will give you when you train it with this kind of data. So this is a better way of selecting models, of selecting regularization parameters, and so on. It's a more robust way of doing this kind of selection. After you select it, then you need to obtain your final hypothesis. And for that, you use the whole training set and obtain the final hypothesis. Just remember that at the end, if you do this, all of these estimates become biased. So if you want an unbiased estimate of the true error, you need a testing set. We also saw this problem of stratified that we can solve with stratified sampling, which is the problem of when we are splitting the data at random, we can end up with greatly imbalanced subsets of data. So if you use stratified sampling, you avoid that. I recommend that you read section 2.7 of Alpine, but basically these are, and you'll see there these ideas, cross-validation, so on, explained a bit better. But these are basically the important aspects of this lecture.